This is CPE 133, Introduction to Verilog Modeling. This is Part B, Chapter 4 from the Free Range Verilog Foundation Modeling text. So in the previous Part A, we started looking at our first Verilog models, which we implemented simple circuit, did it a couple different ways, introduced the notion of continuous assignment statements, which was simply an assignment statement. The assign statement anyway. For this, we want to continue onwards and want to introduce the notion of scalars and vectors. And so the previous examples, all the data signals were 1 bit wide, and those are referred to as scalar signals. And now we want to use vectors, and that's essentially a signal other than a 1-bit signal. So it's a multi-bit signal, and so we typically refer to these as buses or bundles. Now I like to use bundle, though a bus is quite popular. The issue with buses, it actually means something else in digital design. It's more, it can mean protocol as well as a group of signals. So the issues here are how to declare bundles, how to use them, and particularly how to access the individual signals within the bundle. So this is just a chunky little example. It's just essentially what this is doing is taking two 4-bit signals and ANDing them together. Now it's easy to say ANDing two 4-bit signals together. What it's actually doing is doing a bitwise AND. So these two inputs X and Y are 4 bits wide. I know that by the notation that I use here. The square bracket notation, 3 down to 0, that means there's 4 signals in there. The labels of those signals are 3, 2, 1, and 0, which is 4. So all the two inputs and the outputs have the same width, which is 4. I've arbitrarily, but a good idea, declare them 3 down to 0. So 0 is going to be the index of the rightmost signal, or the least significant bit. 3 is going to be the index of the leftmost signal. This particular example doesn't really use the individual signals. It's using the signals as 4-bit vectors. Okay, so essentially it's taking the 4-bit X vector, bitwise ANDing it to the 4-bit Y vector, and assigning the result to the 4-bit W vector. So there's no reason in the world I'd have to use 4 assigned statements in this model. I could, but no one ever does that, and you shouldn't do that either. So I want to generate another simple example here, and we'll work through this. And it's essentially, the point of this example is to show you how to access the signals within a bus or a bundle. So essentially this circuit here has a 4-bit input and it has 3 outputs. So the 3 outputs essentially give a status regarding the 4-bit input A, and essentially the 3 status outputs indicate when the input is greater or equal to 12, when it's less than 8, and when it's greater than 3. And the notion here is that we're assuming that the A input is a 4-bit unsigned value. So let's crank through this. There's not really much cranking to do, but the issue is I'm just going to plop this example down and describe it. So the first part of any solution is, of course, to generate a black box diagram, which is in the previous solution. But the next thing we do is we generate the external interface, which is the inputs and outputs of the module. So that you can see that the input A there is a 4-bit vector, or a bus or bundle. The other 3 outputs are each 1 bit wide because I don't specify exactly the width of them. Once I don't specify the width, it's going to default to a 1-bit signal. So this kind of exercises, there's 3 assigned statements there, of course. There's going to be 1 for each output. So the GTE greater than or equal to 12 output is going to indicate when the input's greater than or equal to 12. And the way I'm going to do this is to say that the 2 most significant bits of this value, and I should be able to draw this, but I don't. Actually, my tablet is broken at this point. I'm waiting for a part to come in. Essentially, the A3 and A2 are the two most significant bits of that 4-bit value. So if what I'm doing is ANDing those together, if those two bits are 1, then GTEQ 12 is going to be a 1. So if A3 and A2 are both 1, that it doesn't matter what the other two bits are, that value is greater than or equal to 12. So the A operator there, the A square bracket 3, A square bracket 2, gives me a way to get at the internal signals of that A vector. For the next assign statement, I want to know when the value is greater than 3. So that means if either A3 or A2 are set, that value is greater than 3. The other two bits, once again, don't matter. And the last bit there is I want to know when, the LT8, I want to know when that input value is less than 8. And so what I'm doing is complementing the A value. So if A is 0, that means the most significant bit of A is 0. It doesn't matter what the other three bits are. Even if they are all 1s, that would only be a 7. So if what I'm doing is complementing the most significant bit, if the most significant bit is a 0, it gets complemented and it becomes a 1. So LT8 becomes a 1 when A3, which is the most significant bit of A, is a 0. So these are kind of 3 little tricks to make this circuit work, and there's actually probably better ways to do this, but once again, I just want to show that these are the ways you get at the interior of these bundles. These are, of course, continuous assignment statements. So, summary of this chapter: there's 2 approaches to modeling circuits: high level, which is behavioral modeling, which we didn't do in this chapter, but we did work on some low level modeling. We call those high-level modeling behavioral modeling. We've arbitrarily called this low-level modeling or this gate-level modeling data flow modeling. There's 3 parts to TP, not to a Verilog circuit: the external interface, the internal circuitry in the internal interface. The external interface is what the outside world sees. The internal circuitry is the modules within that circuit, and then we connect those modules within that circuit using the internal interface. So the heart of data flow modeling is the continuous assignment statement, which was that assign statement, and as we saw in this later example, Verilog worked with both scalar and vector data types.